Imagine you are scrolling on social media and suddenly you see a post that looks real, but it's actually misinformation clearly spread. Or think about a fraud detection system in a bank. One tiny trick in the data and the system completely misses the fraud. These problems are not just random errors, they are often connected to the underlying models we use, and one of the most widely used models in such scenarios is a graph neural network or GNNs. Now, here's the issue. GNNs are powerful, but they are also fragile. They they can be flooded with very small changes like adding or deleting a few connections in a graph. On the top of that, they act like black boxes. They give us predictions, but rarely an explanation. This makes them hard to trust in sensitive applications. That's where our project comes in. Hello everyone, I am Ch.Jithender presenting on behalf of team G615. My team members Meghana, Anjali, Surya and Chinmay. Our team mentor is Dr. Shilpa Gupta. Our project is called Framework GNN AID, Graph Neural Network Analysis, Interpretation and Defense. In simple words, the framework is about making GNNs stronger, resistant to attacks, safer, reliable to critical applications, more sustainable. So we can see actually trust in the decisions. With this we are aiming to build a we are not with this we are aiming to build not just a better GNNs but also more trustworthy AI system for the real world. Understanding the base paper GNN AID. The base paper we studies is what really gave you the foundation for this project. It highlights an important fact. While there are many frameworks that deals with interpretability and interpretability secure for models in images, text, or tabular data. When it comes to the graph data, things are far less developed. The paper introduced the idea of GNN AID, a framework that focuses specifically on graph neural network and tries to make them interpretability, robust, and secure. What stood out were a few key contributions. It tries to bring everything together analysis, visualization, and defense into one single framework. It does not just stop a data set, it also provides tools for visualization and even a web interface. So the researchers can interface with the models. Most importantly, it points out with the big challenges. Sometimes defenses against one type of attacks can actually weaken defenses against another. This means robustness and interpretability aren't just add-ons. They need to be carefully balanced. The This insight really motivated us. We realized that if we want GNNs to be trusted in the real world, we need to undefined solution that looks at all three aspects together: analysis, interpretation, and defense. Thank you. Problem definition. In artificial intelligence today, one of the biggest concerns is trustworthiness. People are using AI in finance, healthcare, social media, and even secure systems. But here is the issue. While many frameworks already exist on image, text, or tabular data, when it comes to the graph neural networks or GNNs, is this area it is very still underexplored. This leaves us with big problems. First, GNNs behave like black box. They give us predictions, but we often don't know why the model made that choice. Without explanation, it is very hard to trust them in critical applications. Second, they are vulnerable to attacks. Even small changes like tweaking connections between the nodes or slightly modifying node features can completely fool the model. This makes them unreliable in real world scenarios. Third, there is no undefined framework. Existing tools deal with either interpretation or analysis or defenses, but none of them bring everything together in one place. And finally, practical gap. Current research solutions are not user friendly. There isn't a simple, accessible platforms where people can easily visualize how attacks and defenses work on GNNs. So, our problem definition is clear. If we want GNNs to be useful in a real world system, they can't give predictions. They need to be explainable, secure, and trustworthy, all within one defined framework. Now, let's dive into the architecture of our framework GNN AID. We begin with the input layer, which consists of a graph datasets. For this milestone, we are working with the standard benchmark datasets like Cora, and in the later stages, we will move into the larger ones like OGB. These datasets represent a real-world graph structure such as research papers and the citation networks. Next, we move on to the model layer. Here, we build the train different GNN architectures, GCN, the classic graph convolution network. And then next GAD, which uses attention to focus on the most important neighbors. And then GIN, graph isomorphism network, knows as a strong structural representation. And then after GraphSAGE, but not the last, which is the powerful and inductive task predicting for unseen nodes. Once the model is trained, they enter the attacks and defense layer. Think of this as the stress testing lab. On one side, we perform attacks like poison, aviation, or privacy benchmarks by twisting node features or graph edges. On the other side, we apply defenses such as adversarial training and sanitization to see how well they hold up under attack. In parallel, we run the interpretability model. This is where we use explainers to highlight why a model made a certain decisions, identifying which nodes, edges, and substructures influence the predictions. This adds transparency, which is crucial if people are going to trust the outcomes. Finally, all the flows into the visualization and web interface. Instead of just giving accuracy numbers, our framework provides interactive visual insights, allow users literally to see how attacks impacts the model, how defense protect it, and what factors influence the predictions. Behind the scene, the pipeline is powered by PyTorch geometric for model building, Network X for operations, and a no-code web interface that makes the framework accessible to both researchers and non-experts. So, in short, the architecture is like complete journey. Data goes in, models are trained, attacked, defended, explained, and finally visualized in a clear and understandable way.